Hello, everyone. This is the lecture for section 3.8, implicit differentiation. So this is one of the harder sections for chapter 3 and in Calc 1 just in general. We are going to, first of all, find out what it means to have an implicit function, okay? And then how to proceed to do the derivative for these implicit functions, okay? And we're going to be using all the stuff from chapter 3 that we've learned up to now. Okay, so for section 3.8, okay, there's going to be a sort of a distinction that's going to be made. Okay, and that distinction is going to be something that is implicit versus something that is explicit. Okay, so up to now, okay, and I mean up to now from kindergarten all the way to today. Okay. You've mostly been messing around with explicitly defined functions, okay? Specifically, something that looks like this, okay? You've been messing around with functions that are of the form y equal some function of x, okay? Where the y variable is entirely and completely defined, okay, by a function comprised of the x variable. Okay, so that if you plug in a value for the x, you get a y value. Okay, unfortunately, in math, this is not the case. Okay, there are going to be times where, in order to define the y variable, you need the output from the y variable in order to do it. So it becomes a little circular. Okay, um, those kind of functions. Okay, where the definition of a variable depends on the variable itself, okay, are things that are called implicitly defined functions, okay? So there's our distinction. Explicitly defined functions is where you can actually say y equals stuff, right? And implicitly defined function is where you can't do that, okay? So what we're gonna do, all right, so this is the re-recording of this particular section. There was a section in section 3.8 when I was doing the edit where the audio was just not good at all. I sounded very muffled. You couldn't hear what I was saying. So I'm deciding to just redo the section that was missed. And it was basically from here and doing the explanation of the three explicit functions that we have here, at least the more commonly used ones. So let me go ahead and explain these again, okay? And I'll stick this back into the video. Hopefully it doesn't look too bad of an edit. Pretty sure it's gonna be okay, but I'd rather erase it in front of you, at least on video, and redo them really quick, okay? So like I was explaining, these are the three most common sort of implicit functions that we're gonna be using, okay? The first one is a circle. Okay, and the circle has this sort of form, right? So if you have an H and you have a K, that's automatically going to be the center, and then the R squared, whatever that is going to be the R right there. It's going to be a radius. So that's how we do a circle, okay? The next one is an ellipse, sort of like the circle, right? Just a little different. The H and the K give you the middle of the ellipse, right? And then the A gives you that A, and the B gives you that B. So, and this is how you get your ellipse, okay? Now, hyperbola works out sort of like the same way. And I'm gonna go ahead and label this how it's supposed to be labeled. So that point right there is gonna be your H comma K. That's gonna be your middle. So it works out the same way as the circle and the ellipse. The H and the K are those two things right there, okay? The next thing is going to be the A. The A tells you how far up, or sorry, how far left or right to go. That's your horizontal distance, right? That's what the A does, okay? And the B tells you how far up and down to go, okay? From that point, okay, so that's what the A and the B do, A and B. From that point, you get to draw this square. This square right here, okay? That square right there. And then you sort of draw lines through these vertices, 1, 2, 3, 4. Notice how these blue lines right here, notice how these lines right here, let me see if I can go ahead and draw lines through them. Notice how these lines go sort of straight through, right? There's one line, and here's the other line. Trying to draw them as nicely as possible, but you see the point there. So those two lines go through those green corners there. And from there, the actual graph of this function is actually this right here. See these two swooshes? Let me actually go ahead and do them in a purple highlighter. You guys see these swooshes that are right there? Those purple swooshes are the actual sort of graph of a hyperbola. Okay, now, if you guys take a look, the difference between a hyperbola and an ellipse is this, just the plus and the minus. Okay, got it? So just make sure you know which one you're looking at before you go ahead and jump, start jumping into it. Okay, now let me go ahead and do an example again. I know it's done right here. Let me go ahead and re-explain it with full audio so that everybody can hear what I'm saying. Okay, so we know that this thing has a negative. You guys see the negative in between, right? So since this one has the negative, not the positive, it is not an ellipse. It is a hyperbola. Okay, this gives us, if you guys take a look, this is a +3. So these sort of operate opposite of the sign. So if it's a +3, you know that the center is going to be that -3. This is a -2, so it's 2, +2. So then that gives us our point right here, 3, 2. -3, 2, -3, 2. Look at me go. Okay. And then if we take a look, 25 is 5 squared. So that means our A is 5. Okay. 9 is 3 squared, which means our B is 3. Okay. So that means our A tells us to go sideways, right? Horizontally, 5 spaces. And that's what happens here. I go 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay. And then the 3 tells us we need to go 3 vertically. So up 3, down 3. Okay. That produces our box. So if you guys remember that box that we had to draw, here it is. We have our box. Okay. Once our box is done, we connect sort of opposite corners, right? Remember this thing. We had to draw these two lines, these two thick lines right here. That one and this other one that goes the other direction. Those are going to be sort of what it's going to amount to our asymptotes for this graph, okay? And then finally, our final little thing is to put the two swooshes, this one here and this one here. Once those are done, we are done. This is our graph thing. Okay. What I want everybody to notice is if you take a look at, I'm not required, but you're more than invited to try this. Go ahead and grab any one of these functions or any one of these expressions and try to solve out to get y equal to stuff. Okay. One of two things is either going to happen. You're either not going to be able to flat out, right? Or you're going to have two equations that you're going to have to mess with. Hence the reason why we have this distinction between implicit and explicit functions. In order to write any one of these expressions, we have to do it implicitly. Okay. From here on out, I think this is where it continues. Please make sure you do your the quick checks that come after this. I will be looking at answers a little later. Okay. Quick checks. Go ahead, do the one that's assigned to you. Okay. So what I want to sort of, now we're going to get into implicit differentiation. Okay. So how does implicit differentiation work? all the stuff that we've been doing at the moment has been geared toward explicit functions, as in we have a y equal f of x, right? We haven't found the method for implicitly deriving stuff. How do we take the derivative of a graph that we've seen from above, right? How do we actually find these derivatives? Okay, and the answer sounds like we're cheating, but it actually sort of works out. Okay, to take the derivative of implicitly written functions, okay, uh, we do exactly this right here. We assume that the portions of the y variable can be written explicitly, and then we use chain rule without knowing what they look like. That's why it sounds like cheating, right? I know that it sounds very confusing, okay? But this is the overall sort of like behind the scenes, under the hood theory that's happening. We are essentially assuming that it is explicit, using the chain rule and seeing what pops out. Okay, that's the theory behind it. So what usually people remember is just whenever you take the derivative of y, you also have to write in y prime. Okay, so what do I mean? Let me go ahead and do this. So find the equation of the tangent line of the following expression at the point, that one right there, and verify my answer using the graphing utility. Okay, so I'm going to go ahead and take the derivative of this, right? Eventually, somewhere in there, and you guys will see what I'm talking about. Okay, so the first thing we need to know is what the heck is this thing asking us for? It's asking us to find the equation of a tangent line. That's exactly what I'm going to do. So my final answer somehow, some way, is going to be y equals mx plus b. We know how this works out, right? We need to find the m first and the b second. Okay. So now the m becomes our most difficult part because we need to do the derivative of this implicitly. Okay. So here we go. So I'm first going to rewrite this a little bit. I'm going to rewrite it like this: 1 over 25 times x plus 3 squared minus 1 over 9 y minus 2 squared is equal to 1. All I did was rewrite. Okay. Here's the calculus. I need to take the derivative of both sides. Okay. So that means I need to grab this, right? Take the derivative, and then take this and take the derivative of that. Okay. Because of our sum and difference rule, I can take the derivative of both of these portions, this and this. I can take them separately and then add them together. So that's exactly what I'm going to do. We know how to take the derivative of this already, right? So it's going to be 1 over 25. So the constant's out front, just gets to come along to the right. And then I need to take the derivative of this thing right here. And that's going to be times 2x plus 3 times 1. So that's going to be a chain rule, right? So drop the 2 down, and then the derivative of the inside is just 1. So we're all done with that one. Okay. Here comes the fun bit. Minus, I need to take the derivative of that next portion, the one with the y in it. Okay. So like I said, whenever you take the derivative of the y, you just need to make sure that you're doing the chain rule, which means you need to take the derivative, you need to sort of write in y prime. Okay. So here we go. This is what I mean by that. The 1/9 gets to stay. That's a constant number, gets to come along to the right. I'm going to take the derivative of this thing right here. It's exactly how you think it is, times, I'm going to drop the 2, y minus 2. Okay, that's the chain rule. Okay, so now I need to take the derivative of the inside. If I take the derivative of the inside, which is y minus 2, the derivative of that is going to be just y prime. This is what I mean. Okay, and that is it. We are done there. Is equal to the derivative of 1, which is 0. So let me denote what I did. This derivative right here is this portion right here. And this derivative right here is this portion right here. Okay. From here, the interpretation is just as you remember it. We need to find y prime. That's our derivative. That's going to get us the slope of the tangent line. Okay. So our goal now is to find that y prime. You can do anything you want so long as you get y prime by itself. So that means I'm going to grab all of this stuff, move it over to the other side. So it's going to be minus 1/9 times 2. Let me actually clean that up a little bit. Minus 2/9, right? Y minus 2 y prime is equal to minus 2 over 25 x plus 3 times 1. So we're good, right? Last big step. I notice that all of this is multiplied already. This is a multiplication too. So if I could just divide this away over here, I get y prime by itself. So divided by minus 2 over 9, y minus 2, divided by negative 2 over 9, y minus 2. We get y prime is equal to, and I'm going to do a bit of reducing here, 9 x plus 3 over 25 y minus 2. And we have our derivative. So now notice this derivative is a lot different from the ones that we've been messing with from before. In order to find the slope of the tangent line, we need both the x and the y to find the m. Okay, so that's exactly what I'm going to do. Notice, remember, we have a point to use, and that's exactly what we're going to do. So then that means the m is going to be my y prime, right, at this point right here. 13, 13, whoa, no, sorry, 9. My x, which is 13 over 4 plus 3, all over 25 times y, so minus 1/4 minus 2. This is going to be, there's going to be a lot of mass in here. So it's going to be 9, 13 over 4 plus 12 over 4 divided by 25 9 over, negative 1/4 minus 8 over 4. Nine times 25 over 4. 25 times negative 9 over 4. And if you do this right, you should get negative 1. So what we just did was m. So now it should be a little easier to go ahead and do, right? Since we found m, we found part 1, right? We can now find b. So our equation, let me write this in here. This is part 1, right? This next part is part 2. Okay, so we know that our equation is going to be a y equals m minus 1 x plus a b, right? And it's got to go through this point right here, the 13 over 4, comma negative 1 over 4. So off to the races. So my y is negative 1/4 is equal to negative 1. 13 over 4 plus b. This multiplies to negative 13 over 4, so I get to add it to the other side. So minus 1/4 plus 12/4, oh, sorry, plus 13/4 is equal to b. So therefore, b should be equal to 12 over 4, which is 3. The final answer now, y is equal to negative 1x plus 3. And we are done. Okay. I'm going to do this really quick too. Okay. So the crux of this all, right, is to do, so whenever you take the derivative of y, you also have to do the y prime. That's the portion of the chain rule. Okay. So now, to verify that this is true, okay, thankfully, we can still do stuff on Desmos. So let's go ahead and open up Desmos. I'll show you guys how to put stuff in. Okay. Turns out we can put in this equation. So I'm going to go ahead and do x plus 3 squared divided by 25 minus y minus 2 quantity squared divided by 9 is equal to 1. So notice how this is set up already. Okay. The problem was at 13 over 4 comma negative 1/4. So I'm going to go ahead and zoom in on 13 over 4. So 13 over 4 is about past 3 a little bit. So about right here. Right? And we want it at negative 1. So it's actually down here. Sorry. Right here. Something around here. So actually right there. Okay. So it's at this point where we want it to be tangent. We have an answer. We just get to graph it and see what happens. So I'm going to go ahead and plug this in. Our answer is minus x plus 3, right? So y equals minus x plus 3. And lo and behold, it looks pretty tangent to me. Look at that. There we go. So 3.25 right there. That looks pretty tangent to me. Unfortunately, the calculator that I provided for you guys, in order for it to do implicit differentiation, that needs a human head. So Desmos cannot actually do the derivative for us. The only way to double check your work is by doing the graph and actually plotting the tangent line. Okay, so that's why I'm showing you guys how to do it this way. All right. Okay. So we know now how to take the derivative of implicitly defined functions. Okay. This, like I said, it's about the same as when we learn how to take the derivative of something with the chain rule. Now that we know implicit differentiation, a bunch of other functions and expressions are open for us, so we can take the derivative of them very quickly, relatively, okay, and do some cross. Okay, so what comes up next is switch up. So all I want to do here is just find the slope of the tangent. So these are explicitly implicit defined expressions. Okay, implicitly defined expressions. And I just want you guys to find the slope of the tangent. So find y prime. Not those points that I did. Okay? They should be nice enough. So you get something a little wonky, maybe you get a fraction. A fraction's okay, but if you start getting decimals, yeah, that's, double check your work. Okay. So let me censor this a little more. Okay.
Okay, so now we have, now that we know what implicitly defined functions are, how to take the derivative, right? Let's open it up. Let's go ahead and do, let's go ahead and go toward much more difficult, much more complex uh, functions. Okay, so find the equation of the tangent line for the curve just right here using your graphing utility to verify our answer. Okay, so same idea. We need mx plus b. That's 1, and this is 2. Okay, that's the order we're going to go through. So 1. I'm going to go ahead and rewrite this just to, I'm not going to modify it at all. I'm just going to keep it as it is. Y times sine of 2x is equal to x times cosine of 2y. Okay, so notice what we have here. Both sides of the equal sign are products. So that means we need the product rule for both sides. Okay, so let's go ahead and do the left-hand side first. So the derivative of this, right? If you guys remember the derivative of a product, it's the derivative of the first times the second plus the first times the derivative of the second. Okay, that's the order. So let's go at it. So the derivative of the first, so the derivative of y is just y prime. So this is a, remember how I told you guys, take the derivative of y prime all the time. Okay, times sine of 2x plus y times the derivative of sine of 2x. And that's going to be times 2. The derivative of sine is cosine of 2x is equal to. Now I get to take the derivative of the right-hand side. Okay, and to do that, again, product rule. So the derivative of the first times the second. So it's going to be 1 times cosine of 2y plus the first times the derivative of the second. So the first, now the derivative of x, sorry, I went the wrong way. Plus the, times the first plus the first times the derivative of the second. So this is going to be x, let me go ahead and do this, x times the derivative of the second. So here we go. The derivative of something that's cosine is going to be negative sine of 2y. This is a chain rule, right? So then I need to take the derivative of 2y, which is going to be times 2y prime. Okay. So I'm going to rewrite this a little bit and get rid of the multiplications that are in there a little bit. So this is going to be y prime sine of 2x plus 2y cosine 2x is equal to cosine of 2y plus x, let me change that, minus x, minus 2y prime x sine of 2y. Okay, this looks nasty. Very much so. Okay. If you remember from example 1, what we needed to do at this point is gather everything so we can get y prime by itself. We are solving for y prime. Okay. So that's exactly what we have to do here. We have to gather everything that has the y primes in it and put them on one side, and gather everything that doesn't have a y prime in it and throw it to the other side. So what I'm going to do is I'm going to collect the y primes on the left-hand side of the equation. okay? And then everything else is going to go to the left-hand side of the equation, okay? So if I do this, this is the only thing, this right here, is the only thing that has a y prime on the right-hand side. I'm going to throw it to the left. So this is going to be a plus 2y prime x sine of 2y. So I need to add it over here. Plus 2y x of 2y prime x sine of 2y. This is the only thing on the left-hand side that doesn't have a y prime. So I'm going to throw this to the other side. So it's going to be minus 2y cosine 2x minus 2y cosine of 2x, right? So this cancels on this side, and then this cancels on this side. So what I have left now, I'm going to rewrite it in all its glory, okay? Y prime sine of 2x, that's what we had from before. The next thing is going to be what I sent over from the right-hand side, plus 2y prime x sine of 2y is equal to cosine of 2y minus 2y cosine of 2x. Okay, so notice what I did. Everything with a y prime is on the left-hand side, and everything without a y prime is on the right-hand side. Okay, I am going to now factor out a y prime. So what do I mean by that? I'm going to grab this. I'm going to do this right here. Y prime. Making nice and neat. Y prime. If I take y prime out of this, I just get left with sine 2x plus, and if I take out a y prime from here, it's going to be 2x sine of y is equal to cosine 2y minus 2y cosine of x, 2x. Okay? So now all I get to do is I get to divide by all of this. And that'll get us our y prime. And I forgot it too. Great. So m. So this is going to be my third time doing this because I've let this be a lesson to everybody. Keep a track of your x's and y's and all of the constants and make sure you're writing them all over. So the first mistake that I made, let me point those out, was that this was supposed to be sine. I had it down as cosine. And the second mistake is that I forgot this too. Okay, so like I said before, there's lots of spots where you can mess up. Just double check your work. If something doesn't work out right, something's not looking right, go back and check that you're carrying everything over, because I didn't. So okay, so let's go ahead and find m now. Finally, cosine of 2y, so 2 times my y, pi over 4, minus 2y, and my y is pi over 4 here, right? Times cosine of 2 times x, pi over 2,
all over sine of 2 times x, pi over 2, minus 2x sine of 2 times my y, pi over 4. Okay. This is going to put a big strain on your pre-calc, specifically your unit circle. So if you don't have one, make sure you get one, at least have it out on your desk, okay? So you can reference them, okay? So I'm gonna go ahead and start computing this out. Cosine of 2 times pi over 4. So the cosine of 2 times pi over 4, 2 times pi over 4, that's gonna be pi over 2. Cosine of pi over 2, that is 0. Minus 2 times pi over 4, we know that's pi over 2, times cosine of 2 times pi over 2. So this is going to be cosine of pi. And cosine of pi, that is minus 1. All divided by sine of 2 pi, 2 times pi over 2. 2 times pi over 2 reduces down to pi. So sine of pi, that is 0. Minus 2 times pi over 2, that's going to be minus pi, that's what that reduces to, right? And then sine of 2 times pi over 4, so 2 times pi over 4 reduces to pi over 2. Sine of pi over 2 is 1. Okay, and this reduces down to, and I forgot a positive here, that's my bad. Yet another mistake. Ooh, I'm on a roll. 1/2. So if you do all this math right, you should get m is equal to 1/2. Okay, we're not done yet because we have to find the equation of a tangent line, but we're almost there. So that means our y has to be 1/2 x plus b, right? At pi over 2, comma, pi over 4, the point that was given to us from before. So now we get to plug in values, right? So pi over 4 is equal to 1/2 x pi over 2 plus b. Pi over 4 is equal to pi over 4 plus b. B's got to be equal to 0. And what did you do that for? Get rid of that. Yeah. Okay. So then our final answer now. Y is equal to 1/2 x plus 0. And we are done. I know this is a long way coming now, but here we are. So the tangent line to that curve at that point should be 1/2 x. So again, you can always use a graphing utility to verify your answer. And thankfully, Desmos is pretty good at graphing these things. So let's go ahead and go back here. I'm going to go ahead and get rid of that and get rid of that. I'm going to make this a little more. There we go. So our function was y times sine 2x. 2x is equal to x cosine of 2y. Let me zoom out so you guys can see what this thing looks like. This is going to be one of the wildest graphs you guys will ever see. Okay. We need the curve of we need the tangent line at this point right here, pi over 2, comma pi over 4. That's about right here. Okay. So we're going to go ahead and graph it. Y equal 1/2 x. And lo and behold, there we are. Actually, let me change this, the steps, to pi over 4. There we go. So pi over 2, comma pi over 4, that's that point right there. You guys can take a look at it. So it does look like it's tangent there. Okay. There we are. Okay. So I'm going to have you guys do a couple more examples here. Okay. This one only has odds and evens. So if you're group 1 and 3, do the top one. If you guys are group 2 and 4, you do the bottom one. Okay. So now that we know how implicit differentiation works, we're going to go ahead and use it to prove these. So if you guys remember, the inverse sign, the derivative of inverse sign is something that looks like this, right? And when we looked at this section, we just took them at face value. We just said, these are the derivatives. We didn't question them, and we moved on with our lives right now. Now we know how to take the derivative of one of these. Okay, we're going to need implicit differentiation to do it. Okay, so the first thing I'm going to do, okay, is let me get my notes ready. Okay, so we know that what I'm going to do first is I'm going to do this. I'm going to say y is equal to sine inverse x. Okay, if you recall from pre-calc, I can invert this. I can say that if y is equal to sine inverse of x, then that means, right, that if I do sine of my function y, whatever it is, that should be x. Okay, and this is going to be an x over 1, right? So what I'm going to do now is I'm going to draw my triangle. If you guys remember how these things work, right? Here's my triangle. Let me draw it correctly. There we go. Right triangle. Okay. So then that means this right here is my y. That's my angle, right? Sine is opposite over hypotenuse. So that means it's going to be opposite. This is going to be my x over 1. That's why I had to write it over as x over 1. Okay. And if we use Pythagorean theorem, we get this expression for this bottom bit, 1 minus x squared. Okay. So we have the triangle now. Okay. We have our triangle. So now we're going to go ahead and take this. I'm going to take this bit, and we're going to do implicit differentiation on that. So I'm going to go ahead and grab this. I'm going to do an arrow this way. So we're going to do sine of y is equal to x. So now I'm going to do the implicit differentiation. So I need to take the derivative of that, derivative of that. The derivative of sine is equal to, if you guys remember how to take the derivative of trig functions, right? Derivative of sine is going to be cosine of y. Since we're doing chain rule, this is going to be times y prime for the implicit differentiation is equal to the derivative of x, which is 1. So then that means, I'm going to go ahead and just separate y prime out. Y prime is equal to 1 over cosine of y, right? Here's the fun bit. Cosine of y. This is where we're going to use our triangle again. So cosine of y is adjacent over hypotenuse. Okay, so from the triangle, right, cosine of y is adjacent square root of 1 minus x squared over 1, which is just root 1 minus x squared. So then therefore, y prime is equal to 1 over 1 minus
square root of 1 minus x squared, right? All that's left now, really, y prime, y was equal to sine inverse of x. So then therefore, right, sine inverse of x derivative is equal to this right here, 1 over the square root 1 minus x squared. So all of these inverse trig functions, the derivatives for them work out sort of the same way, okay? This is how you prove these inverse trig functions, okay? And I believe that is it for this section, because after that comes lecture questions. Yeah, okay. If you guys have any problems with these, if you guys want to ask me questions, like I said, I have a drop-in online hours that you can come visit me. I am in person in the math lab, or we can schedule something outside of those times, okay? Besides that, I hope to see you guys around.